Hello everybody, and welcome to this lecture on computer architecture. Today I want to talk to you about memories, namely latches and flip-flops. So let's take a look at how this works. First of all, I want to remind you that until now we have been working with the so-called logic arrays, meaning that the output of a circuit actually depends only on the input signals of the circuit and there is no memory effect. We did this by designing gates, using gates and designing with the sum of products and products of sums and Carnot maps and so on. We implemented any logic function we could come up with. But now we're going to make the circuit a little bit more complex, and we will see the emergent property of memory. And this happens in this case. We will introduce feedback into our circuit, and then the emergent property is that it will have memory. And this is the entire idea, that every time we make the system more complex, there will be emergent properties coming up. And in this case, we are going to do feedback, and we will see that we'll get memory effect. So let's see how this works. I've put here. I already put here remember the NOR gate, which we're going to use here in this set reset latch, a memory element. So remember the NOR gate. It is 1 for the input combination of 0, 0. Otherwise, it is 0. And now I have used two of those beasts and linked them up in such a way that I have one input is the set and reset, S and R as they're called, and you will see in a moment, you will see why. And the thing is that the output of one is then fed back into the input of the other. And now we get this kind of behavior. Let's assume we have here 0 at the output here, and as you'll see, the other output is always not the inverted of the other. And this one is fed back into the first, so we get here 0 and we get here 1. And now imagine I apply a 1 to the S, to the set, and a 0 to the R, to the reset. So I'm talking about, no, not this one, not this one. I'm talking about this input combination, while the output state is 0 at this moment. So let's see, 1 NOR 0, that is 0, so this changes to 0. Hey, but wait a second, then this one also changes, so this one becomes 0 too. And now we have here 0 NOR 0, hey, that is 1, so this one changes. But this one is fed back into the first one, so this one is no longer 0, it's 1. So now let's see, 1 NOR 1, that is 0, that's okay. And we have here 0 NOR 0, and that's 1, that's okay. So after a while, it takes maybe a couple of feedbacks, loops. So after a while, when we apply the combination 1, 0, the output becomes 0, as you can see here. Now let's take a look at the other combination. I will erase all these things here. Imagine that we had the output was already after a set, and now I apply reset 0, 1. So this 0 is fed back here, and this here 0 NOR 0, that is 0, that's okay. And then 0 NOR 0, 0 NOR 1, that is 0. Oh, so this one changes, and this one now also is fed back into the first one. 0 NOR 0, that is 1. So this one actually becomes 1, fed back into the second one. This is 1. 1 NOR 1 is 0. So now we have a stable situation. 0 NOR 0 is 1. 1 NOR 1 is 0. So after a while applying this 0, 1 combination, set, reset, indeed the output is reset. So these two combinations are very interesting, very easy to understand. But now let's imagine that I have the 0, 1 combination at the output, and I apply 0, 0. What happens now? 0 is applied to the input here, 1 is also applied to the input here. 0 NOR 1, 0 NOR 1, that is 0, that's okay, that's stable. And 0 NOR 0, that is 1. Okay, so apparently when I apply 0, 0, if I have the output equals to 1, it will stay 1. And what now? Let me put it in blue here. If I can ask me to put blue. No, I want paint. What now if the output was a 0 and the not output a 1? What happens then? Okay, and I apply here again the same 0, 0 to the input. This 0 is fed back here. This 1 is fed back here. 0 nor 0, that's 1, that's okay. And 1 nor 0, that is 0. That's also okay. So if I had a 0 at the output, it will stay 0. So if I apply the combination 0, 0, it doesn't matter what the state was. If it is 0, it stays 0. If it's 1, it stays 1. So I have a memory element. If I apply 0, 0, the memory is contained. If I apply an S, 1, and a reset 0, then the output becomes 1. If I apply a set 0 and a reset 1, then the output becomes a 0. So I can write the state by a set or a reset, and I can actually keep the state by applying 0, 0. And this last combination actually is not allowed, or it's called an invalid input, because then the output becomes both zeros, which is not desirable. It's not a nice state for engineers to talk about. So this one we should avoid the 1, 1 input. But you can see the effect. When you apply feedback, you have a memory element. More often, however, what we want is so-called gated devices, meaning that the output can only change when there's a clock signal, or in general a gate signal applied. If the clock signal or the gate signal is 1, then it's okay. It lets through, and the AND gate here in front of it, it lets through the the set signal, and also here the reset signal. So the stage, the next stage, then is our normal set reset flip-flop. No, sorry, latch. We're still talking about latches. But if I put here, however, if I put here, it doesn't want to change the color. If I put here a 0, so if the clock is low, then I have a 0 at this end and a 0 at this end. And this one will not be let through. This one will be both 0, because 0, whatever is the other input, doesn't matter. The output is 0. And we have in the stage of our set reset flip-flop latch, we have 2 zeros. And that means that the state is maintained. As you know, it doesn't matter then what the real set and resets are. These are not passed through the flip to the latch, and the state is maintained. So this is what we call a gated set reset latch, meaning that the signal, the output, can only change when the clock is high. However, very often we want to define much better at what time the changes take place. So how do we do this? I have to erase this. So now we take the clock and put it into a NOT gate, an inverter, but this inverter also has a small delay, and this delay then causes a small shift in time of the inverted signal. And then at the AND gate we have the clock signal which arrives directly, and we have the NOT clock signal which arrives a little bit later. So we get this situation. The clock signal, and then we put an AND signal, the NOT clock signal, and as you can see, for a short time both of them are high, and this determines then the width of the output signal after the AND gate. And if this delay is very short, this pulse can be very short. We're talking about, let's say, maybe a picosecond or something like this. And to represent this in our schematics, especially in our flow diagram in time, we represent this with this arrow, that actually the state of the outputs of the circuits that we're going to use, they respond, or they change upon the edge of the pulse. And the edge is then the beginning. For instance, in this case, the rising edge, but it can also sometimes be with another schematic. You can also use it at the falling edge of the clock pulse. The clock pulse itself is symmetric, duty cycle of 50%, so there is no problem in that. But the states of the outputs, the circuit itself is responding to the rising edge or to the falling edge. And let me then show you how this is then used. In this JK, what we now talk about is a JK edge triggered flip-flop, because the flip-flop actually is responding to the changes of input states rather than the states itself. Then we call it a flip-flop. So the difference between a flip-flop and a latch is that it is responding to the state itself of the inputs or to the changes of the states of the inputs. And in this case, when we use that trick of ending the clock by the delayed clock itself, then we call this a flip-flop. And that is the most famous circuit. In this case, the JK edge triggered flip-flop. We also indicate this by this triangle here. It means it's edge triggered. Edge triggered. And the idea with the JK flip-flop now is that we have this set reset flip-flop, but we put a stage before it which is ending the SR, which are now called JK. S set reset signals, we are ending them with the gate, the clock, and we are actually putting another feedback that the output is also fed back here to the input of the ending stage. And as you can work out yourself, just pause the video and do some calculation. If you have the input JK equals to 0, it maintains the state. If you have the input 0, 1, it is like the reset of the set reset flip-flop. If you put the input 1, 0, it is actually setting the output and unsetting the not output, of course. And now the difference between a set reset flip-flop and this JK flip-flop is that the input combination 1, 1 is also allowed, and this actually then toggles the output. So if we had here a 1 and we had here a 0, and if we now apply here 1 and 1, actually this one will become 1 and this one will become 0. Just work out this schematics and apply it. It takes a little bit too long time to present this here, so that's why I will not do this, but just write it down and you will see that it works like this. Now finally, to finish this lecture, this flip-flop we can actually use in two ways to for simpler flip-flops. I want to put this visible here. So if I take this JK edge triggered flip-flop and apply a signal both J and K equal, actually that I exclude these two possibilities where J and K are different, so I can only apply 0, 0 or 1, 1. So I can only actually keep the state with 0, 0 or toggle the state with 1, 1. So this is what you get here. If I apply a 0, the output is maintained. If I apply a 1, the output is toggled. That's why we call this a flip-flop. Another combination is that I invert K. So K is always different inverted from J. So that means that we have the combination, input combination 0, 1 or 1, 0. Now if the input is 0, 1, then as you can see here, remember 0, 1, then the output is 0. And if the input, I want another, it allows me to take another color. So if the input here is 1, 0, then as you can see 1, 0, then the output is 1. So actually what this is doing, it is just copying the input. If it's 1, it copies to the output 1, and if it is 0, it copies to the output 0. That's why we call it a data flip-flop. It seems to be a little bit stupid to just copy the output. Why not put a line here? Why not just put a line? But don't forget that it can only change the state upon the clock. So we have a clocked memory element. By the time the clock signal arrives, then it is going to be saved in the flip-flop. Thank you for your attention.